the previous lecture on sensing, that means sensing part 1, we have gone through the use of different types of sensors for different industrial applications. We have seen sensors such as temperature sensor, accelerometer sensor, gas sensor. There could be different other several different types of sensors, and in typical factories, smart factories, we are talking about the use of large number of different variants of different types of sensors. The beauty about these sensors is that particularly for industrial applications, not only they are supposed to sense whatever they have been made to sense, but also they will have to withstand the harsh environmental conditions. They will have to withstand. So, they have to be robust enough, right. They have to be robust enough to withstand the harsh environmental conditions, the industrial conditions in which they are going to be deployed. Keeping that aside, we have also seen that, as I told you in the previous lecture, that the designing and fabrication of a sensor is a multi-month, multi-year program, and it is a completely different ball game if you are trying to come up with a sensor for the first time. Those who have already come up with a design and it is a well tested, well proven principle, that is simpler. Basically, all you need to do is, once you have a proven concept, you take it and you go for mass production. But for the first time, if you are coming up with a unique type of sensor, the designing of it and fabrication of it is quite complex and is typically done by researchers who take interest in microelectronics, sensor fabrication and so on. That is completely different. But I thought that let me give you a brief idea about one of the sensors, the gas sensor. Along with a colleague, we have taken interest in IIT Kharagpur to build gas sensors and deploy them for monitoring the air quality. So, in this particular lecture, I am going to run you through this kind of sensor, the efforts that we are taking and taking together. Basically, as I told you that the expertise is completely different that is required to come up with a gas sensor. So, I am going to talk about the working principle of a gas sensor, and then I am going to take you to one of the labs of one of my colleagues who is basically fabricating a gas sensor at IIT Kharagpur. A gas sensor basically plays a vital role for monitoring the concentration of flammable, combustible, toxic gases in the environment. Gases such as methane, NOx gases, SOx gases, these are toxic and are very dangerous gases. So, they will have to be detected, monitored continuously. If we are talking about air quality monitoring is very important in today's world, because the entire world, throughout the entire world, somewhere less, somewhere more, the air quality has degraded due to the emission of lot of harmful gases into the environment. So, the quality of the concentration of the different gases, harmful gases like NOx gases, SOx gases, etc., methane, etc., these will have to be monitored continuously, so as not to risk the individuals, the humans living on the earth and other organisms living on the earth, so as not to harm these individuals from exposure to these harmful gases that are emitted in the environment by different automobiles. So, there are different methods for gas sensing. Gas sensing basically can be done with the help of optical methods, acoustic methods, chromatographic methods, calorimetric methods, can be done with moisture absorbing materials, carbon nanotube based materials, polymer materials and metal oxide semiconductor materials. These ones basically are the electrical variants. That means that these type of gas sensing methods like these ones, they look at the change in the electrical properties of the environment where these different gases are. Changes in electrical properties like changes in the current characteristics, changes in the voltage characteristics, changes in the resistive characteristics of the material, the environment where these harmful gases are or the concentrations are raising, and these then basically send these different signals in the form of resistance values or resistance or current or voltage or whatever. These methods basically are the different other methods. So, we will look at in little bit more detail about how to fabricate a metal oxide semiconductor based gas sensor, because that is the facility that we have in our campus, and I can brief you little bit about this particular method of metal oxide semiconductor based gas sensing. So, this is this MOS gas sensors working principle. These MOS gas sensors are chemi-resistive gas sensors. Chemi-resistive means like there is some chemical reaction that happens with the sensor material that is there, because of which the resistive property of that material will change, and what is required is to measure this resistive property with changes in something, maybe change with time or whatever. So, you get the change in the resistive property of that particular material when the concentration of the gas increases, right. So, that means that you need to have specific selected materials for targeting specific gases. It is not like one material will be able to sense large number of different types of gases, it is not like that. So, these are basically selective materials for selective gases, and these selective materials will have the the change in the resistive properties with the change in time or change in temperature or whatever. So, basically we need to understand this chemi-resistive property, but before that we need to understand the concept of the baseline resistance. This is basically the resistance of the sensor material in air when it is not exposed to the target gas. So, this target gas could be, let us say, methane, right. So, when it is not exposed to methane, what is the baseline resistance? This is something that is required to be calculated, or to be you need to have this information. And then this chemi-resistive gas sensors will depend on the thermal energy for its operation, which is basically supplied through some heater, right, because this chemical reaction will have to take place, for which the heater will heat up that particular material, and then that will help in changing the resistive property. So, a particular temperature at which the sensor gives the best response will have to be taken, that is the optimum temperature. So, the resistance value basically changes when the material is exposed to gas depending on the rise or fall in conductivity of the sensor material. So, the choice of the particular material is very important depending on the gas that is being targeted to be sensed. So, in N type sensors basically the resistance increases, and in P type sensors the resistance increases, in N type sensors the resistance decreases, and in P type sensors the resistance increases with respect to the baseline resistance when that particular material is exposed to a target gas. So, there are different characteristics of the gas sensor. Changes in the sensitivity, that means it is the change in the output signal with respect to the unit change in the input. Input means the target gas concentration. If you are changing the target gas concentration, unit concentration change, how much is the unit change in the output signal with respect to it. Selectivity is the ability to detect a particular gas in a mixture of different gases. Stability characteristic is basically the parameter which determines the robustness in the gas sensing property of a gas sensor in a long duration of time when it is exposed to hostile ambience. Response time is the other characteristic which basically captures the time taken by the sensor to stabilize its response when sensing the target gas to reach some percentage, some predefined threshold pre-configured value like 80%, 90% or whatever. So, how much is the time taken to come to that stable point, that is the response time. Reversibility is whether the sensor resistance can return back to its base resistance value if you stop the exposure of the target material to the target gas. And the response percent is the parameter which is calculated by computing the percentage change in the resistance when exposed to target gas with respect to the resistance when it is not exposed. So, resistance when it is not exposed versus this thing, that is the response percent. So, gas sensors find different applications. What I was telling you is air quality monitoring. Likewise, it could be used, these sensors could be used for leakage detection of toxic gases, even leakage detection of LPG pipes, manhole or sewage treatment plants. Gas sensors are commonly used. Automotive exhausts also use lot of gas sensors, different types. Alcohol breath test also use gas sensor. So, I am going to show you the demo of one of these sensors which is based on, it is a gas sensor which is able to detect the presence of volatile organic compounds. So, as soon as basically in these kind of sensors, as soon as the gas sensor senses these gases, their resistive capacities, their resistive properties change with respect to the baseline resistance. That means, when the resistance value when these gas sensors are not exposed to the target gas. So, as the resistance changes, basically alerts are generated if a certain threshold is crossed. This is the overall block diagram of a gas sensing system. We have this sensor module which will have this sensing material for a particular target gas. So, gas basically is passed through this particular sensor module, and this material is chosen in such a way that it is going to change its resistive properties with respect to the concentration, increase in concentration of the chosen gas. Then you have the analog temperature controller which will basically monitor or control the temperature variation, because I told you that we need to have some heater in order to start these chemical processes of these materials when the gas is passed through them. So, that the controlling of this temperature is done through this particular controller, the analog temperature controller. Then you have some kind of a microcontroller which will help in doing some processing of the data, the analog or the digital data that comes into the microcontroller, and then some kind of alert like some buzzer or something could be used in order to generate the alert. So, this will be like an actuator, right. And then you also have kind of a PC which will help you in the overall monitoring and processing. It could be a PC or a laptop or anything, any other computational device. We are actually right now in the gas sensing facility lab of the Material Science Center of IIT Kharagpur. This particular lab is led by Professor Subhashish Basu Majumdar. So, I have with me Professor Basu Majumdar. Professor Basu Majumdar, could you please tell me what are the facilities in this particular gas sensing facility lab?
In fact, the lab was developed to test a variety of gas sensing materials. So, as you know that the gas sensing materials are characterized first in terms of its porosity and semiconducting properties. So, once you have the material ready, then you will have to characterize them in order to know that what is its gas sensing capability. So, we have fabricated a sensing facility which we call a dynamic flow gas sensing facility, because the gases are flowing. So, it starts with this kind of different types of gas we actually procure from outside, and the idea is to make say air quality monitoring, that is one of the examples, or you can sense various types of toxic gases as well. So, at present our lab is interested to measure the sensing facility of hydrogen that you can see, and various toxic gases like carbon monoxide, methane, then NOx, and recently we have started working on carbon dioxide for breath sensing development, breath sensor development. So, it starts with a variety of gas, and there is a provision for you to mix the gas also. So, gases are transported. So, it is having a manifold there. So, you can select that which gas chamber will be connected to the sensing chamber. So, we will have to move from this place to the other side of the lab, and so the gases that are coming from the manifold, there are 4 different lines, and one exclusively we use for the carrier gas, and in most of the instances the carrier gas is air, which is having 20% of oxygen, and a variety of test gas. So, this gas controlled, they are controlled by this mass flow controller, and at present there are 3 mass flow controller, and we can add 1 or 2 more, and this is controlled by this controller. So, the flow rate of these gases you can control either manually or through software, and this pass through a hygrometry chamber. So, we use different types of solutions to maintain the humidity of this gas. So, either you can test this gas in dry condition, or you can put your own humidity to see the effect of gas plus humidity, and this flows through several valves are there. So, it passes through this kind of line, so which is the input line of the sensor chamber. So, we put our sensing element inside this chamber, and I can just take it off the first part, and you can see that there is a small substrate here, and this is connected with 2 probe, and later I will show you the type of sensor that we develop. And just at the point of this base we have a thermocouple, so we can precisely monitor the temperature of the sensing chamber itself, and by controlling this mass flow rate of these gases, we can precisely control that what will be the ppm level of these gases inside this chamber. So, this is blocked initially, although it is not being operated now, but if you just fix this one. So, it is a gas proof chamber with a heater embedded at the bottom. So, we can precisely change the temperature, and your sensor remains there, and 2 probe on the surface of the sensor, they take the resistance value as a function of this gas concentration or as a function of temperature. So, there is a temperature controller. So, in one kind of measurement I can keep the temperature of the sensor constant. So, we call it as an isothermal condition, and then change the gas concentration. So, that is one set of measurement, and we measure the surface resistance of the sensor as a function of time. So, this is one type of measurement. The second type of measurement is that you keep your gas concentration constant and vary the temperature. So, as a function of temperature you can measure the same set of resistance transient, and if you want to make this system complicated, then you can add humidity into it. So, you want to know that at humidity level that how this gas sensing is being performed. So, these 3 measurements are done for each of these samples, and on top of that you can now modify your samples. For example, you start with zinc oxide, then you can add indium into it. So, see what kind of vacancies are there inside this material, and how the gas sensing is changed by porosity or by defect concentration. So there is a once you get this resistance transient value as a function of temperature, as a function of concentration, or as a function of humidity, then you have a wide pool of data, and we do a lot of data analysis of the resistance transient, and we have dedicated equipments for those kind of measurement. And the basic measurement that we do with an electrometer. So, we have two electrometers here. One is a source measure unit, and another one is a very high resistive measurement type electrometer. So, usually we use this electrometer to measure the transient, that is the base data that we measure. So, these are all DC measurements. So, we have the capability to go for AC measurements. So, we can do the impedance spectroscopy by this impedance analyzer, and that will tell us that what is the difference between a DC measurement and an AC measurement, and we can analyze our data perfectly, because sometimes we use the data in the time zone, or sometimes we use the data in frequency zone. So, just by Fourier transform it. So, this gives us lot of flexibility to understand this gas sensing material, and I will show you some of the graphs, that typical graphs which we can think of. So, this part is quite useful, both this resistance measurement and this transient measurement. And also we have another network analyzer, which basically we use for noise spectroscopy, because sometimes the noise inside the resistance transient, that also gives lot of information. This is not very frequently used, but this gives very exceptionally high quality data as far as understanding of the types of gas is concerned, because basically when you measure the resistance versus time, the data is more or less very monotonous. When you pass gas, then the resistance changes, and depending on the concentration of the gas, the resistance changes more. So, you can calculate the response percent from this transient data, that how much is this change, resistance in air and resistance in gas. So, it is Ra minus Rg by Ra. So, you can calculate what is the response percent. How much time does it take to this kind of fall? Typically, according to the ASTM specification, the fall 90% of this resistance at each concentration of the gas. So, that is your response time. Similarly, when it comes back from this resistance to the base resistance, so that is your recovery time. So, these are the basic data of whatever we get, that is response time, then response percent. So, when you do as a function of temperature, then as you can see that not at all temperature it has similar kind of response percent. So, depending on the concentration of the gas whatever you are using and the temperature, operating temperature of the sensing material, you have this kind of bell shaped curve, and this also gives us lot of information. So, I think we can explain it better, but it is a time consuming process. So, you will have to learn a lot of things to understand these basic features. But once you get this kind of data, it will be interesting for you to know that the type of sample, that the morphology of the sample has immense influence on this kind of data, which is one good part, because you can do a one-to-one structure and property correlationship. This particular poster you show, it is being showed that if you have powder, you make a pellet out of it, make two electrodes and then measure this resistance and change your sample configuration from here to a nanotube kind of thing, or a basic thin film, or a embedded nanostructure, or a thick hollow flame nanostructure. These are all schematically drawn, and one-to-one correlation you can get in the upper microstructure. You see that this is just like a pellet, this kind of powder with having a porosity. The tube exactly, it forms a hollow tube, and certainly the gas will diffuse inside, also absorbed outside. So, response percent is very fantastically high here. Similarly, we have nano rod, thin film. This is interesting, a embedded nanotube structure. Already the base is some kind of porous material, and we packed this kind of tubes inside and put one electrode here and one electrode there. So, in that case it is a parallel kind of plate configuration we are using. Sometimes we get the surface type of electrode we deposit. So, once you do this kind of nanostructuring, the same material, same gas concentration, same humidity, same temperature, but you get dramatically improved gas sensing performance. So, the whole idea of this type of dynamic analysis is to understand your material, modification of your material for a particular purpose. In order to make it selective, we also do another type of material prepare. Whatever we do, that is nothing but materials engineering. The same zinc oxide, it can sense all the gases, or by certain modification I can make it selective for hydrogen, selective for NOx. So, this is a tremendous materials engineering we do in this lab, and we get a selective sensor. So, once we get the selective sensor, then the idea is to pack this selective sensor in the form of indigenous sensing element that was developed by our MTech students. So, this kind of sensing element, and then separately we will have to define an electronic circuit module, so that this can be connected with this circuit module, and whatever this all these instruments are doing, in fact that will lead to a portable sensor. So, you can carry this sensor module. So, our job is mostly to manipulate the materials, check their sensing properties, but somebody should make this sensor also to make a prototype, so that we can take it outside, hang it somewhere. So, some kind of arrangement was made. So, that is quite rudimentary, but this kind of arrangement was made, and you can hang it on your wall, and then you put say room fragrance in the wall, and in principle it will do the characteristics. Will do the sensing. Now, one important aspect of this kind of dynamic measurement is that in real ambient this flow will not be there. So, the flow whatever we are getting, so whether this is say 20 SCCM or 100 SCCM or 500 SCCM. So, you are drawing lot of oxygen onto a sensing surface, and when the gas senses, sensing product develops and you are driving it out. So, you get a very characteristic response and recovery plot out of this measurement, but your actual sensor, whenever it will be hang somewhere, there will be hardly any flow. So, we will have to devise, we had to devise a static chamber. A static chamber where you just put the sensor, put some gas and allow it to sense, and then automatically gets recovered. So, that challenge we took when we understood this material well, and this part whatever you are seeing, so much equipment etc., everything was bypassed, and we have our own microcontroller based circuitry, and this was also remotely sensed. So, all this kind of complications came, and it was beyond our knowledge to actually address this kind of practical problem. So, we started to collaborate with different faculty members. One Professor Mishra is one of them, that who is taking care of the remotely controlled sensing. If you can control the sensing, or you can take the data acquisition. Some other faculty member from electronics department, Professor Shudeep Nag, he is working on the development, because in our knowledge we could only do it, but he is an expert in this field. So, he developed a printed circuit board. Maybe in other forum we will show those kind of things, whatever has been developed from this lab. So, material is the heart of this kind of activity, because finally you will have to sense selectively a gas. You should know what is their concentration, and you know exactly that with temperature how it is varying. So, if this temperature is too high, you need a separate power circuit to drive those kind of sensor. So, those are the issues. So, using that feedback we do something to reduce this temperature. This is part of our research, And this is the thing I feel that it is enough for someone to understand that what exactly is done in this laboratory. Now, you will have to make the sensor as well. I mean, this is not only the material, but sensor in different forms. So, we have the facility to deposit a thin film by sol-gel technique, and mostly we use it. In the other lab, we have a microwave assisted hydrothermal technique where we can make porous material or different types of nanostructured material to know their gas sensing properties.
Thank you so much, Professor Basu Majumdar. So we are going to have a look at the other facility that we have over here, where we will see how volatile organic compounds could be sensed.
Yeah, that is one that in case of volatile organic component, it is difficult to get the cylinders for all those things, but you can easily have your gas lighter and you can put butane gas in it. You can easily have some kind of paint where toluene is there. So, just we have developed a chamber. Maybe one of our students will explain it better because she is in the way of in the process of developing it. So, we will just go there and see that how these VOCs are being sensed in this laboratory.
So I am going to now introduce to you Ms. Sarmistha, who is a PhD scholar jointly being supervised by Professor Basu Majumdar and myself. So Sarmistha, could you please explain the setup that you have for sensing volatile organic compounds like methanol, butanol, etc.?
Yes, actually the gas sensing setup is broadly classified into two types. One is dynamic and statics. Dynamic system is already explained to you by sir, and this is our static chamber. Through this one we are introducing the gas through this hole, and there is a sensor array data can be taken through this. We can take multiple sensor data from those probes that are there. We will keep an array of sensors there and we can take data, and this is a real time gas sensing system because it is exposed to real time environment. Here the conditions are isothermal, but here as it is exposed to environment, so this is basically a miniaturized version of gas sensing system. This is the gas sensing probe where you can see we have this is a heater. This nichrome wires you can see within a mica sheets that separates provides insulation between that heater and the sensor. This is a sensor, and this is a NTC, that is a negative temperature coefficient material. It is a NTC thermistor actually used for sensing it is used as a temperature sensor, and mostly it also obstruct the inrush flow of current to the sensor. And then you can see this is a temperature controller. Here a PID control unit is used. We have designed a PID control circuit here, and then through this NTC which I said, as the temperature of that material is increasing, the resistance is decreasing. So that is some way acting as a feedback to the system. So depending on that, the power that is the power transistor which is there, the input to that is varying, and depending on that we are able to control the temperature at a particular at a particular point at which we will perform our experiment. So now you can see this is the baseline for this sensor. This first of all, this is our sensor. This is fabricated on a glass. The base material is a glass, and then using sol-gel technique, we have using a spin coating unit, we have developed a thin film of copper oxide. This is a p-type MOS metal oxide semiconductor sensor. So I'll show you how is it working. First of all, when at a particular optimum temperature this probe is exposed to the environment, the oxygen reacts with the surface of this sensor. So there is some chemical chemi-adsorption process taking place on the surface, due to which we are getting the electrons. This is a p-type material, so the minority electrons that are there, those are taken up by the oxygen, which has higher affinity towards the electron. So what is happening, the conductivity of the p-type material is increasing. So we can see whatever the voltage level we are getting here, it will be the highest voltage. After I introduce A VOC, this is having some ethanol This freshener actually has some ethanol content, which is a VOC. So this particular sensor will detect this VOC. So let's see. You can see the response there, it is falling, the voltage is falling, and it is able to detect that there is a volatile organic compound there in the environment. Depending
So thank you, Sharmishta. So Sharmishta, could you please tell us now about the different applications of these kind of sensors?
Yes, these kind of sensors are widely used in different kind of industry. For example, if you go for oil and gas industry, the workers working there are exposed to different harmful gases there. The diesel engines that are used to run the machineries there in the oil factories, those emit such radiation. The exhaust that are emitted contains very harmful gases like hydrogen sulfides, nitrogen oxides, all those things, and some particulate matters. Those are very much harmful for humans. It may cause lungs cancer, respiratory diseases, and also while in battery fabrication, there you may be exposed to emissions of carbon monoxides and carbon dioxide. At those places, monitoring the concentrations of these gases are very much important. So there are even more wide scale use in different kind of industries of these gas sensors.
Thank you, Sharmishta. Thank you, Professor Basu Majumdar. So these are the references finally, and if you are interested about the design of any of these types of metal oxide gas sensor, this is the one that you could go through, and there are many other references as well. So depending on your interest, you could go through any of these different references. Thank you.